support reactions for this indeterminate beam with a distributed load of W. Hi everyone, welcome back to Fundamentals of Engineering with Farhad. Mechanics of Materials supports reaction for our beam. Let's see how we can approach such problem to calculate the reaction at A, reaction at B, and also the angle created at the B, which is theta B. So the first solution is integration method from the elastic curve. So it just says if we want to integrating our elastic curve to calculate the elastic curve, and then based off the equation of elastic curve and theta, we can get the reaction. So if we cut our beam through by the length of x, and then develop the moment equation at the length of x, and develop the moment, like in our case, this is the entire beam. If we cut it through by the length of x from the fixed support, a moment created, we call that m sub x. And if we calculate that moment, so summation of moment about x goes 0, including mx, and it just says mx plus wx squared over 2 plus ma minus ra times x, counterclockwise is our positive arbitrary direction, goes 0, and it just gives us m sub x equation. So as soon as we have mx equation, we can go for the other part of our puzzle. So in the entire beam, we can have, if we call this equation 1, and from the free body diagram of the entire beam, it just says summation of Fy goes 0. It just says the two reactions of Ra and Rb should cancel out the effect of the resultant of this distribution force over the entire span. So summation of Fy goes 0, it just Ra plus Rb, the two reactions should cancel out the WL. And then summation of moment about A goes 0, considering MA, it just says MA minus WL squared over 2 plus RB times L equal to 0. So in such case, we can have a equation for our, let's put it this way, we can have like the equation for our MA. And if you remember, in the first equation, we have like MA. It just says if we call this equation equation 2, and if we simply replace 2 in 1, if we just have like our MA replaced in equation 1 and rewrite the equation for MX is like this. Rewrite the MA rewrite the MX based off parametric value for moment at A. It just gives us the mx equation is a negative wx squared over 2 plus ra times x minus wl squared over 2 plus rb times l. If we call this equation the third equation and move on to calculate our delta function. So this is our third equation, and we do know that d squared y over dx squared is equal to m over ei from mass and from mechanics of materials. So it just simply says if we integrate moment equation, we can get to this equation, and we call it equation 4. And if we integrate it once more, we can get to the equation of ei times delta. And how we know this? So d squared y over dx squared is m over ei, and if we integrate it once, we reach to, we call it y double prime. Integration of y double prime gives us y prime, which is theta, and that's nothing but the integration or area under m over ei. And if we integrate it once more, and also we can show it like this, if we just rearrange the equation, it just says ei times theta is equal to ei times dy dx, like what we have here, and that's again an integration or area under m. So this equation, it simply says integrate or area under moment for once. And if you integrate it twice, it just says if you integrate y prime or theta, you reach to y, and y is equal to delta, and that's integration of theta or ei delta ei y. That's double integration of moments. So that's double integration we reach to from the third equation, we reach to fifth equation. So by each of the integration, two constants added. So if we integrate it twice, we have two constant of integration. Now let's jump to the boundary condition. So we do know that at the very beginning of the beam, x equal to 0, there is no theta, there is no delta. That's our, we call them A and B. That's our two first boundary condition. And also at x equal to L, there is no upward or downward flip-flop. So that's our third boundary condition. We call it C. And then if we just consider our first boundary condition, A and 4, it just simply says at x equal to 0, theta is equal to 0. This is the equation of theta. It just simply says if you replace all x by 0, it just gives you C1 is equal to 0. And likewise, if you go with the second boundary condition, b and 5, so at x equal to 0, delta is equal to 0, that's our b boundary condition. B and 5, it just says replace all the x in the fifth equation by 0, it just simply gives you a c2 equal to 0. So we have yet one other boundary condition to use in the next part of the problem. So this time we are focusing on C and 5. So C boundary condition C talks about if x is equal to L, delta is equal to 0. So this is the equation of delta. And so C and 5, it just simply gives us another equation which relates RA and RB. If you remember, at the very beginning of our problem, we had like RA plus RB should cancel out the distributed load over the span. So if we solve this set of equation simultaneously, we can get the reactions of RA and RB. So how to do that? We can easily see if we just simply multiply the top equation by a negative 6, it just gives us a negative RAL cubed. And if we just multiply the below equation by a L cubed, it just gives us RBL cubed. Then we can cancel out RA from the top and bottom. So this is the first equation after multiplication, and this is the second equation. And likewise, you can easily see these two are cancelled, RA and RA cancelled, and then it just gives us a negative 3/4 WL to the 4 is equal to a negative 2 RBL cubed. And if you solve this equation for reaction at B, it just gives you 3 over 8 WL is equal to RB, and likewise RA and RB should equal to WL. If you replace that bar by RB, it just gives you RA is equal to 5WL over 8. And that's also makes sense because you can easily see the reaction at A carries a bigger chunk of the load in comparison to reaction at B due to its fixed nature. And the other part which we want to calculate, we can easily go for calculation of theta at B. At x is equal to L, theta is equal to theta at B. We have the equation for theta, and if we just replace x by L and RA and RB directly into our equation, it just gives us theta at B is equal to WL cubed over 48 EI. Thank you. We'll solve this problem with different approaches, with three different approaches in next videos. Thank you.